Hi, my name is Tyler, and I'm going to be presenting a 12-bit SAR ADC with 11-bit ENOB. This is for ECE714 at NC State. Here is the high-level architecture. I'll be going more in depth into the transistor level design of the charge redistribution DAC, which is binary weighted split array, the track and hold samplers within that DAC, and then the latching comparator after the DAC. The SAR logic finite state machine was implemented as an ideal behavioral block using Verilog A. Here are the system calculations for the DAC. The thermal noise from KT over C in the DAC sets the total size of the capacitance in the DAC. It needs to be able to meet the quantization noise floor, which is around delta squared over 12. Using the full scale range of 300 millivolts and assuming a 12-bit DAC, I calculate this quantization error. To meet this quantization error noise constraints, I need to have this total capacitance of 9.3 picofarad, which is calculated below. This results in a unit capacitor of 2.3 femtofarad, which is unrealistic and is not supported within the design kit and cadence. As a result, a split array was chosen to increase this unit capacitor to roughly 145 femtofarad. The split capacitor was calculated to be roughly a unit capacitor, which I'll go into more in the next few slides. So this is showing the design and initial simulation results for the DAC. The design is right here. You can see the split capacitor is roughly a unit capacitor, and it lies between the LSB array and the MSB array. You can see it is also binary weighted, and I have a dummy capacitor. The DAC at the top, which leads out to the comparator, is using a simple complementary T-gate track and hold switch running at 30 megahertz. The other switches down here driving the capacitors are bootstrap, which are running at 400 megahertz. They have to run at 400 to achieve a effective SAR ADC rate of 30 megahertz. The initial simulations using ideal switches are in the top left plot. The signal to noise and distortion ratio was 71 dB. I calculated that to be around 11.5 bits. This sample rate is 400 megahertz with an input of 250 kilohertz. I then substituted the non-ideal switches and received about a half-bit ENOB degradation. And the ENOB degraded significantly in the final transistor simulations, which I attributed to the use of poor switching, so I had to replace them with bootstrap switches. Here are some simulations for DNL and INL. The DNL is a uniform distribution, and there's this plot. The max DNL is a tenth of an LSB, and the plot on the right is the INL, which is not a uniform distribution, which is expected. The max INL is about 0.7 LSBs, which is less than 1, which means that there are no missing codes. Here are the system calculations for the track and hold sampler. The finite acquisition time plays a significant role, and in order to meet a 12-bit resolution with half LSB settling time, I need at least 9 time constants I've calculated. Using this 9 time constants and the 400 megahertz clock rate for the bootstrap switches, I calculated the time constant to be needed to be less than 0.14 nanoseconds. The simple T-gate switches running at 30 megahertz can work up to 1.85 nanoseconds on the other hand. Using these time constants and the total capacitance I calculated earlier, I can calculate the on resistance required to achieve both these capacitances and time constants. For the bootstrap, I need the total capacitance of each switch to be less than 15 ohms, which is extremely small. And also needs to be very stable with input signal. That's why I had to implement a bootstrap switch. On the right is the on resistance for the T-gate switch, was around 200 ohms, which is more reasonable. On the left side is the design for the complementary T-gate track and hold sampler. It's running at 30 megahertz. It is essentially a 4-to-1 mux without a fourth input. So it is acting as a 3-to-1 mux and is comprised mainly of inverters and complementary T-gates. On the right is the 400 megahertz bootstrap T-gate track and hold sampler. It is also comprised of inverters and complementary T-gates. There is a boot capacitor right here that is applied to the VGS of the output switch, leading to a constant VGS, which leads to a very stable on resistance. Here are some simulation results for the track and hold samplers. On the left side is the complementary T-gate track and hold sampler running at 30 megahertz. You can see that the red is the input signal of 30 megahertz, and you can see the green is the output of the track and hold. You can see that the time constant of 1.85 was met with 1.4 nanoseconds. On the right is the simulation results for the bootstrap track and hold sampler. The input frequency in this scenario is 10 megahertz, and the track and hold samplers are running at 400 megahertz in the pink. You can see that this pink is actually the gate voltage on the output transistor, and you can see that there is a VGS of approximately power supply of VDD. So you can see that the gate of the transistor rides on top of the input, leading to a constant VGS, which leads to a very stable on resistance. As a result, you can see that the tau of 0.14 nanoseconds was met with 0.067 nanoseconds. Moving on to the system calculations for the latching comparator. In order to achieve a bit error rate of less than 1 LSB for a 12-bit resolution, my delta needs to be less than 73 microvolts. I also need to compensate for the input referred offset voltage, and I did that by setting the input common mode to the comparator to be the opposite polarity of that offset. The comparator's time constant also needs to be well within the half period evaluation phase, with inputs going all the way down to half an LSB resolution. I calculated at 400 megahertz time constant of less than 0.8375 nanoseconds that my comparator is required to meet. So the design of the comparator is on the left. It is comprised of a simple current mirror with a latching comparator using positive feedback. The reset switch in the middle of the comparator is using a small width to mitigate charge injection and clock feed through. And the simulation results are on the right, and you can see that I've input voltages ranging from all the way up to full scale 300 millivolts down to 50 microvolts, and you can see that the latch time is well within the half period evaluation phase of the clock period. The time constant is less than 0.8375 nanoseconds and is roughly 0.3. Some more simulation results for the comparator. I input a ramp from minus 300 millivolts to positive 300 millivolts, which is in the bottom right plot. You can see that this middle point is the 0 volts, if you will, or ground, and the left side is going down to minus 300 volts, and the right side is going up to 300 millivolts. And you can see that the comparator has switched decisions at the 0 point. This is the plot after I compensated for the input referred offset voltage by setting the input common mode to the opposite polarity. I measured it to be around 29 millivolts. I did a ramp input with a finer step size going from minus 100 microvolts to positive 100 microvolts, and that's in the plot on the left. You can see that this region right here is centered around 0, and it's more of like a no man's land where the comparator is making the wrong decisions. And I measure that to be around 80 microvolts, which is slightly higher than the 73 microvolt 12-bit resolution requirement, although this does meet the 11-bit resolution requirement of around 140. Finally, the SAR ADC nominal simulation results. This is using all Verilog A blocks. I measured the signal to noise and distortion ratio to be 75 dB. That is the plot on the top left with a sample rate of 30 megahertz and an input of 100 kilohertz. You can see that there's a spur here at 30 megahertz, which is the ADC switching harmonic, but overall the E knob up to FS over 2 is around 12 bits, as you'd expect for a 12-bit SAR ADC. You can see in the bottom left plot, I've changed the input frequency to 1 megahertz, and the E knob stayed relatively the same with maybe up to half a bit degradation. You can also see that some intermodulation distortion harmonics have arisen. These are essentially two-tone harmonics, which are basically can be calculated by the sampling frequency plus or minus the input frequency. So the upper spur is around 31 megahertz, and the bottom spur is around 29 megahertz. These can be eliminated with a differential design in the future, because unfortunately I did not go that route with a differential design. Lastly, is the SAR ADC transistor level simulation results. On the top left is the signal to noise and distortion ratio, which is about 68 dB for a sampling frequency of 30 megahertz and an input of 500 kilohertz. This is an E knob of about 11, just above 11 bits, but I calculated the E knob up to FS over 2 to be about 11.5. You can also see the same switching of harmonics at 30 megahertz, and then the DAC switching harmonics around 200 and 400 megahertz. I then set the input frequency to 1 megahertz, and I received a signal to noise and distortion ratio of about 60 dB, which is about 9.5 bits. I gave a few input frequencies ranging from 700 kilohertz to 900 to 950, and they all were above 11 bits ENOB approximately, but it degraded significantly around 950 to 1 megahertz. So I would assume that my effective resolution bandwidth of my SAR ADC to be 1 megahertz, which is my figure of merit. And that's it. I also just wanted to thank you real quick for letting me take your course. Me being a distance student, I know you didn't have to do that, and I appreciated you working with me. I enjoyed this course a lot, and I've actually already used it in my day-to-day job, and I'm probably going to use it in the future, so I just wanted to take a quick moment to thank you. And that's it.